Today, we're diving into what is essentially a classic detective story, but it's playing out on a cosmic scale. Let's call it The Case of the Missing Cosmic Clumps.
And, like any good mystery, it all kicks off with one simple but really nagging question. When we look out at the cosmos, at that vast, beautiful web of galaxies and clusters, we found that it's all just a little bit smoother than our best theories say it should be. So, why?
And this is where our story really begins, with this fundamental conflict, a cosmic contradiction that has cosmologists hunting for clues inside the very fabric of space-time itself.
Okay, so our leading theory of the universe. The one that's been wildly successful at explaining pretty much everything from the Big Bang's afterglow to the expansion of space, it makes a very specific prediction. It tells us exactly how clumpy the universe should be right now, how all that matter ought to have gathered together over the last 13.8 billion years.
This table right here, it just lays the whole mystery bare. That top line, that's our prediction, and it's based on a perfectly frictionless universe. It predicts a clumpiness value, which we call S8, of about 0.83. But then you look at the bottom line. Well, that's reality. That's what our telescopes actually see. The universe is much smoother, with a value closer to 0.76. Now, in cosmic terms, that gap isn't small. It's a giant red flag.
So this gap, it actually has a name, the SA tension. And let me tell you, this isn't just some minor disagreement or a rounding error. It's a huge clue that a key piece of the cosmic puzzle is just missing from our model.
So the big question is, where does this tension actually come from? Well, some fascinating new research is suggesting it all might hinge on a single and potentially completely flawed assumption we've been making about the vacuum of space. For years, the standard way of thinking was pretty straightforward. If things are less clumpy, well, maybe there's just less matter out there pulling things together. But a brand new interpretation from a framework they're calling vacuum elastodynamics proposes something far more radical. It says this isn't an optical illusion caused by missing mass. It's the real, physical effect of a cosmic drag force, a kind of friction that's built into space-time itself, and it's actively slowing everything down. And this quote from the researchers themselves, man, it just hits the nail on the head. By assuming this frictionless vacuum, our models have been, in their words, artificially inflating how much structure we should see. In other words, we've been doing our math as if space-time was some kind of perfect superfluid, when in reality, it might actually have a bit of stickiness to it.
So what's the proposed solution here? Well, it requires us to imagine a totally new property of the vacuum itself, a kind of cosmic drag.
The paper calls this viscous damping, and the idea is just wild. It's that the vacuum of space isn't a true void at all. Instead, it behaves like a physical medium that has a tiny amount of internal friction, kind of like a cosmic molasses. And over billions of years, this viscosity literally strangles and slows down the growth of galaxies and clusters.
And here's where it gets really, really compelling. When you factor this cosmic friction into the equations, the model doesn't just get a little closer to what we see. No, it absolutely nails it. It naturally predicts a clustering amplitude of about 0.753, a number that aligns perfectly with the smoother universe our telescopes are showing us. So the main takeaway here is profound. The SA tension isn't a problem of missing gravity from some mysterious source we can't find. It's the signature of a physical property, friction, that was missing from our models the whole time. We were misinterpreting a kinematic drag effect as a gravitational one. But hold on, because this idea doesn't just stop there. It has these huge implications that ripple out across all of cosmology. Because if the vacuum has actual physical structure and friction, well, that completely reframes another one of the biggest mysteries out there, dark matter. Now get ready for this. In this new picture, we might be able to stop searching for some new, exotic particle we can't find. Dark matter is proposed to be something much, much stranger, lattice vacancies. What are those? Essentially tiny defects, missing points in the fundamental crystal-like structure of the vacuum. Think about that. Dark matter isn't a thing in space-time, it's a flaw of space-time. Okay, that immediately brings up a pretty obvious question, right? If dark matter is just holes in the fabric of reality, why can't we see them? Why can't we bump into them? Why are they so dark? Well, the answer is a property called hyperuniform screening. The best way to picture it is to imagine the vacuum structure as this perfectly ordered crystal. This perfect order is so rigid and uniform that it effectively shields these missing points from the outside world. Light and matter just pass right over them as if they're not even there. The only thing that can't be hidden is the tiny warp in spacetime that their absence creates. And that's what we detect as dark matter's gravity.
And all of this leaves us with a really provocative final thought. This one model seems to resolve the S8 tension and completely redefine dark matter, all by treating the vacuum not as an empty stage, but as an active participant with its own physical properties. So it just makes you wonder, right? If the vacuum isn't empty, what other cosmic mysteries are out there just waiting to be understood as features of spacetime itself?